Let's talk about stringed instruments and the harmonics that can be excited on a string. So I am going to consider a string with length L that is fixed at both ends. And so in this case, only waves with a certain wavelength lambda and certain frequency f can exist on the string. All other waves will not propagate on the string. If such a wave is excited on the string, it's just going to lose energy and die off. So the waves that can be excited on a string are called harmonics. And all harmonics that can be excited on a string form what we know as the harmonic series. So how many harmonics can be excited on a string? Well, they can be many. There is no limit on how many. So here is a representation of the first three harmonics on a string. So this is the first harmonic, which has a frequency that corresponds to the fundamental frequency. Then we have the second harmonic right here. And finally, we have the third harmonic right here. Now let's look at how the three harmonics are generated on the string. So the first harmonic is the wave that has the longest wavelength lambda that can exist on the string, in this case with length L. So here is my string. It is fixed at both ends. It has length L. And so the wave with the longest wavelength that can exist on the string will have two branches. We have a branch with length lambda over 2, half the wavelength, as the wave propagates from left to right. Then the wave will reflect from the right fixed position, and then it's going to go back towards left. And so that generates another branch with length lambda over 2. So over the entire length of the string, we can fit two branches of the wave, each with length lambda over 2. So then that means that for each lambda over 2, I can match the length of the string L, and from here I can express the wavelength of the fundamental wave, of the longest wave possible, of the first harmonic, lambda 1, and that would be equal to twice the length of the string. So then I can also write an expression for the frequency that corresponds to the first harmonic, also known as the fundamental frequency, by using the relationship between the speed of the wave in the string, the wavelength, and the frequency of the wave. And so after rearranging the terms, I get that the frequency of the first harmonic, or the fundamental frequency, F1, is equal to the speed of propagation in the string divided by twice the length of the string. The second harmonic that can be generated on the string has a wavelength that is the second longest wavelength that can exist on the string. So here is again my string. It's fixed on both ends. And now the wave that's generated on the left end is going to propagate on the string or along the string like this. Then it's going to reflect from the right end, and it's going to propagate back towards the left fixed position like so. So each branch is long lambda over 2, or so half the wavelength of the wave. So that means that for the entire length of the string L, I have two branches with wavelength lambda over 2 fitting on that length of string. So 2 times lambda over 2 is equal to the length of the string, and from here I conclude that the wavelength of the second harmonic, lambda 2, is just equal to the length of the string. Again, using the relationship between the speed of propagation, the wavelength, and the frequency of the wave, I can write an expression for the frequency of that second harmonic, so F2, and that is equal to 2 times the speed of propagation divided by twice the length of the string. Finally, the third harmonic is going to be the wave with the third longest wavelength lambda that can exist on this string. So the string again is fixed at both ends, and now the wave is generated from the left fixed position, and then it's going to propagate to the right like so, it will reflect from the right fixed point, and then it's going to propagate back to the left. And so then each branch of the wave on the string has length lambda over 2. And so we can see here that we have 3 times lambda over 2 fitting the entire length of the string. So 3 lambda over 2 is equal to the length L. From here, the wavelength of this third harmonic lambda 3 is equal to twice the length of the string divided by 3. Again, from the relationship between the speed of propagation, the wavelength, and the frequency of the wave, I can write an expression for the frequency of the third harmonic. So F3 is equal to 3 times the speed of propagation divided by 2 times the length of the string. So now we can summarize these results to write 2 general formulas for the wavelength and for the frequency of any harmonic that can be generated on a string with length L. And so the wavelength of any harmonic is calculated as twice the length of the string divided by this number n, where n corresponds to the harmonic in question. So for n equal to 1, we're going to substitute 1 here, and that will correspond to the first harmonic lambda 1, the wavelength of the first harmonic lambda 1. For n equal to 2, that will correspond to lambda 2, the wavelength of the second harmonic. For n equal to 3, that will correspond to lambda 3, so that is the wavelength of the third harmonic, and so on and so forth. Similarly, for the frequencies of the harmonics, we have this general expression. So this general expression. So the nth frequency, or the frequency of the nth harmonic, is equal to n times the speed of propagation of the wave in the string divided by twice the length of the string. So n, again, is this number, 1, 2, 3, 4, so on and so forth. And so each value of n corresponds to the harmonic in question. So for n equal to 1, that would be the first harmonic, or the fundamental frequency. For n equal to, we talk about F2, that's the second harmonic. For n equal to 3, we have F3, so that is the third harmonic, and so on and so forth.